So a Salton similarity is using a different type of, I mean, in essence, it's similar, but the idea we were stating is it doesn't look similar at first. So the idea is that we characterize each node by a vector. So we have two vectors and we want to see how similar two vectors are. So if we want to do that, one idea is to find the angle between two basically vectors. So the angle between two vectors, if it is 0, it means that they're overlapping those two vectors. So those two nodes, corresponding nodes, will be similar. And if the angle between that is large, it's going to be basically dissimilar. So cosine of that angle is a good measure, because if the angle is 0, it's going to give us 1, and basically the other way around. So one idea that people came up with was to characterize each node. The vector that we want to define is the neighborhood of that node. And that neighborhood is essentially defined with a row in the adjacency matrix. So let's say that we want to look at node VM. So the nth row of the adjacency matrix is essentially encoding the neighbors of node n. So it's saying that what nodes are connected to node n, and that's basically giving us a measure of how the neighborhood of node Vn looks like. The same thing can apply to node Vn, and then we use these vectors as vectors representing their corresponding nodes, and we find the angle between these two. So let's write that down. We have the inner product of those two vectors divided by the modulus of each vector. So let's write that in the index notation. When we write it that way, let me show using Cruiser so people online can see as well. Can you see this? No? Can you see this? Okay. So all right, so the idea is that we have our basically inner product. We represent basically vector m and vector n, and we sum over all the elements k of these two vectors. Since adjacency matrix is essentially symmetric matrix and we are talking about undirected graphs. So the adjacency matrix is symmetric. There is no difference between node nk and element nk and kn of adjacency matrix. So we can simply flip the places of these two and we end up like this, right? So then on denominator, we have elements of adjacency matrix. We are finding the size of those vectors, am and an. So we are essentially summing the squares of basically those elements, and basically we are finding a square root of that. Because adjacency matrix is a matrix consisting of 1 and zeros, there is no difference between the square, basically basically 1 squared and 0 squared and 1 and 0. So there's still 1 and 0. For that reason, we can get rid of this 2 here, and we're essentially summing over a row of the adjacency matrix. If I'm summing over a row of the adjacency matrix, what will happen is that I will have the degree of that node, right? It is saying that if a node is connected to that basically node, it's going to be 1. So if I sum all the ones, it's going to be 0. So, I mean, it's going to be the degree. So we essentially have the square root of degrees here. And then we see that in the numerator, now that we have flipped basically the places of k and n, we have a matrix multiplication basically written in index notation. So we write that as, both are a, so we can write that as a squared. And we are looking, for example, in similarity, of nodes I and j, for example, you're looking at element ij of the basically square of the adjacency matrix, and we divide that by square root of the basically multiplication of the degrees of the corresponding nodes. So this has a root 0, right? So if any of those two nodes that we want to see their similarities is essentially does not have any neighbors, if it's disconnected from the graph, then this is not going to be well defined. So by convention, we set that to 0. So a node that has no connections to the graph, its similarity with any node in the graph is going to be 0. So when we say that if basically two nodes, their Salton similarity is equal to 1, means that they are sharing all their neighbors with each other. And we can see that easily from this relationship for Salton similarity. So the basically square root of, the square root of adjacency matrix shows paths of length 2 between nodes I and j, as we discussed in first session. So that means that you basically move from node I to an intermediate node k, and then from that node k to node j. Therefore, both of those nodes I and j share node k. Both of them are connected to node k. So that means that total number of that is equal to square root of their degrees, which, you know, if they're sharing all their if all their neighbors are falling on the paths of length 2, then this guy is going to be equal to 1. So these basically measures are normalizing our equation, our basically function, which is the number of shared neighbors based off of the size of local neighborhood. But the issue is that not all the nodes show the same measure, basically measure of similarity between two different nodes. So let's say that we have a Twitter graph and a bunch of us are basically have a Twitter account and we're following some stand-up comedians. Let's say that we are following Dave Chappelle, we're following Sarah Silverman, and you're also, you know, if you're interested in stand-up comedy, we go to shows in the town as well, and we are following this local guy that performs at Corby's Irish Pub. So the fact that both, for basically two of us, are both following Dave Chappelle means that we're interested in stand-up comedy, but, you know, may mean that, but there are another million people that are following Dave Chappelle on Twitter, and there are another 12 million people that are following Sarah Silverman on Twitter. So, you know, we can just be one of those two people that are, you know, following both of them, right? But the fact that we're both following this local guy here, you know, gives more information that, you know, these people are probably living in that area, or, you know, they kind of probably know each other because that's a local place. Not many people know that, right? So the idea is that if a common neighbor of two nodes has a lower degree, means that there's less other nodes connected to that, it conveys more basically similarity between basically the first two nodes. So the fact that this local guy is a neighbor of both of us is more informative than we share Sarah Silverman and Dave Chappelle as our neighboring nodes. So following this, there are two equations. One is resource allocation, which is summing over all the common neighbors that two nodes have. So it is node VKs that are both a member of the neighborhood of VI and the neighborhood of VJ. So we go over all these shared nodes and we add 1 over degree of them. So in first equation, basically in this figure, Dave Chappelle would add 1/1,000,000th similarity for two of us. So Silverman is going to add 1/12 million, and this local guy is going to add, you know, let's say that he has 500 people following him on Twitter, it's gonna have 500, which is a larger value. So it is basically adding more similarity in this resource allocation equation. And another method is called Adamic-Adar, and they are doing the same relation, basically going over all common nodes that are a member of common neighbors of Vi and Vj, and it's saying 1 over log of the degree is added as the basically similarity between those two nodes.